Chapter 9, Using Functions in Graphics. In this chapter, we examine how to display graphics on the computer using vector graphics. With vector graphics, you draw images using lines and position the lines on the screen using coordinates that determine where the resulting image goes. You will also learn how to move in an image on the screen by manipulating the full color of the image. The functions you learned in Chapter 8 will be very useful in programming graphics. In this chapter, defining graphics, vector graphics, how graphics work, drawing lines and points, examples of functions that generate graphics, typical graphic moves, making a drawing disappear, moving a drawing, delaying the computer, how to call a function. Graphics. How did you do that? One of the coolest things you can do when you first learn how to program is to draw an image on the screen. The topic of graphics brings to mind anything from complicated 3D games like Halo and Final Fantasy to the simplistic graphics used on highway notification signs. In this chapter, we will look at some of the techniques involved in creating and displaying images. By examining older graphics methods, you can feel confident that you will be able to handle whatever newer languages offer in the way of graphics. The method of graphics we will learn is called vector graphics, which derives its name from the meaning of the word vector, a directed line segment. If you can design an image in terms of a sequence of lines, you will be able to show it on the screen using vector graphics. This is not a difficult thing to do. You will then learn how to move that image, something even more impressive. Vector graphics. The word vector implies magnitude and direction. Think of a vector as an arrow that has a length and a direction. Is the arrow pointing down or up or sideways? Imagine drawing a picture with the following restrictions on your drawing. First of all, you can only draw an image with straight lines. What could you draw if someone restricted you in this manner? See Figure 9.1. Figure 9.1. A house is drawn that has only one door and two square windows. Grass on the front lawn is depicted through lines. What if someone forced you to draw your picture sequentially? You would draw one arrow, and then the next arrow would begin where the previous arrow left off. The third arrow would begin where the second arrow left off, and so on. See Figure 9.2. Figure 9.2. A house is drawn as a sequence of arrows joined head to tail to create the final image of a house. Creating an image from line segments that touch each other is an example of vector graphics. In reality, you do not need to have each new line touching the previous one. However, it is helpful to remember where lines begin and end. Drawing lines and points. To draw lines and points, you first need to understand that you are drawing onto a piece of paper, the screen, that has been marked as a grid that has rows and columns. The rows are numbered beginning in the top left at row 1 and column 1 and continuing down to row 2, 3, 4 and so on to row 150, for example. The columns start at the top left and continue to the right for columns 2, 3, 4 and so on, all the way to column 250, let's say. See figure 9.3. Figure 9.3. The screen is shown with an imaginary grid imposed over it to show the positions on the screen. The actual number of rows and columns will depend on your computer screen. Once you understand how the screen has been delineated into these blocks, then you can start to draw. The way to draw is to decide where you would like to start drawing a line. Imagine that you are holding a pen in your hand and you want to put the pen down onto the paper. Where do you want to put it? Let's start by putting the pen onto the block marked 45. That means we have put the pen down onto the paper at row 40 and column 5. We haven't drawn anything until we call on a function to help us draw something. See figure 9.4. Figure 9.4. An X is shown on the position 45 on the superimposed grid on the screen. You cannot see the grid on the screen. Example 1. Let's look at some headings of a function that will be useful for our drawing. Our initial position, 45, is the location on the grid. Let's call those two integers taken together a point. The first function is called moveTo, and we will use it to move to a different point from the one we are currently on, 45. Because it is a function, we need to examine its parameters so that we can call it properly. The value parameters of the function moveTo are two integers, one for the row and column position of the new point where we intend to move. moveTo 45, 50. This call will cause us to move to row 45 and column 50 on the grid. moveTo 5, 5. This call will cause us to move back up to the upper left corner of the screen. Note: recall that nothing is drawn by the moveTo function. We simply are moving to a new position on the screen. Example 2. The second function, line2, takes two integer parameters as well to represent the two coordinates, the row and the column, of the point on the grid where you wish to draw a line. Line2 will draw a line from your present position on the grid to the new position sent into the function. Line 2, 20, 25. In the example, a line will be drawn from our present position, 5, 5, to the new position, 20, 25, as specified by the call to the line2 function. Here are the headings for each of the functions. Void moveTo, int row, int column, void line 2, int row 1, int column 1. Both functions have the word void in the return type position. This indicates that no values will be sent back to the calling place after the functions have been executed. So let's practice using these functions so you can see how they work. The first thing we will do is draw a huge capital letter M. We'll draw this by using the following algorithm. Algorithm for drawing an M. 1. Move to the lower left corner of the letter. 2. Draw a line straight up. 3. From that position, draw a diagonal line down to the middle of the M. 4. From there, draw another diagonal up to the top right corner of the letter. 5. Draw a line straight down to the finish of the letter. The algorithm involves moving to where we want to position the M, and then drawing the 4 line segments that make up the M. The difficult part about making the letter will be judging where the 2 diagonal lines should meet in the middle of the letter M. Find the middle of this letter. The column should be halfway between the left and right columns. Step 1. Move to 45:10 position. 2. Draw a line up to 25:10. That means that our line is 20 units long. That is, it stretches from row 45 up to row 25. Remember, we are moving in a direction as we draw this letter. We are trying to draw in sequence and not just any way that we want. Otherwise, we would constantly have to reposition ourselves by calling the move to function. Step 3. Draw a diagonal line down to row 40, not as deep as 45, and at column 30. Step 4. Draw a diagonal line up to row 25, same height as left vertical line, but at column 50. Notice that these last 2 steps position the top tips of the M 40 units apart. The left tip is at column 10, and the right tip is at column 50. The middle point of the letter, let's call it the vertex, is at column 30. By adding or subtracting 20 columns from this vertex, we get some symmetry, a natural mirror-like quality where one side of the letter is a mirror image of the other. Step 5. Draw a line from the right tip down to the bottom from the point 2550 to 4550. Let's look at each of these steps as a connection of points on a surface. Consider that you map the points first, then afterward you connect them to create the letter M. See Figure 9.5. Figure 9.5. The outline of the letter M is shown as a group of unconnected points on a surface. Now let's list the sequence of steps to draw the letter M that would be used in a program. The first part of the program is to include the library group of files that contains these functions. If you recall, we have already seen the IOStream library, which has the functions that facilitate showing output and receiving input, and the string library, which has the functions that manipulate strings. A graphics library will include these functions that I have mentioned. So let's examine a small program to draw the letter M. The program is not complete because some of the initial commands to open a window on which to draw will vary from machine to machine. # include iostream.h, # include graphics.h. Int main, parentheses, open brace, ... move to 4510. We position ourselves at the lower left corner. Nothing is drawn yet. Line 2, 2510. A line is drawn up to the top left. Line 2, 4030. A line is drawn to the middle of the M. Line 2, 2550. A line is drawn up to the top right. Line 2, 4550. A line is drawn down to the bottom right. Return 0. Closing brace. So we have just drawn the letter M by moving to a point on the grid and then drawing a sequence of lines from that first point through the other points we saw in figure 9.5. Some helpful hints when drawing. In addition to some of the functions we just examined, we need to consider additional functions that help us draw. One of the understood features of drawing when using these functions is that you draw with an imaginary pen. The pen's thickness and color that can be controlled by the programmer through the functions that we will examine next. Using the pen to draw. Before using the pen, we will want to set the size of the pen tip. Imagine that the tip of the pen is a rectangle rather than a point. How big that rectangular tip is will determine the thickness of the lines we can draw. Imagine the differences among pens whose tips are rectangles with these sizes: 2 by 2, 4 by 6, 8 by 10. The smallest tip will be the 2 by 2 tip, and it will not be as big of a tip as the 8 by 10. See figure 9.6. Figure 9.6. Lines drawn with pen tips of varying sizes. First example, a line segment drawn with a tip that is 4 units wide and 6 units high. Second example, a line segment is drawn with a tip that is 8 units wide and 10 units high. On with the text. We set the size of the pen tip through a function called pen size. The function takes 2 integers as parameters, one to set the height of the rectangle and one for the width. Here is the heading of the function, followed by some calls to the function. Void pen size, int height, int width. Pen size 2, 2. Pen size 4, 6. Pen size 8, 10. Later in this section, titled Using Functions to Draw, we will look at the function that allows us to change the color with which we draw. For now, you may assume that we are drawing black lines on a white background. Background versus foreground. It is important to define two terms in graphics, and these are the background and foreground. The background represents the window onto which we are drawing. Usually it is white. The foreground represents anything we draw onto the background. In the section titled Using Functions to Draw, we will look at the functions that allow us to control the foreground color. Note: it is important to familiarize yourself with the graphics functions that are available to you. These functions will be dependent on the hardware of your computer and its operating system. How to make an object move. A nice thing to do after creating an image is to make the object move, that is, appear in a new position. Making an object move uses an interesting algorithm. We begin by displaying the object in some foreground color, called the forecolor. The forecolor is the color with which we draw against the background color, usually white. Then we erase it by drawing it again in the same color as the background. This has the effect of making the object disappear. After that, we draw the image again in its new position. It will appear to have moved. By manipulating the colors with which we draw the image, we can make the image drawn in some forecolor either match the background color or contrast it either match the background color or contrast with it. When the image is drawn in a contrasting forecolor, it is visible on the screen. When the image is drawn in the same color as the background, it will not be visible. This has the effect of erasing the image. Once you practice drawing an image in either the forecolor or the background color, you will start to understand how a programmer gets an image to move on the screen. She will change the image's forecolor to match the background color. Then she will draw the image in a new position with a contrasting forecolor. The image will appear to have moved. But there is another thing to consider. Computers process instructions so quickly that any programming statements used to display images will execute so rapidly that you may not recognize what happens on the screen. So to slow down or delay the computer so that you can see the images as you intend them to look, we add a loop. Let's look at the algorithm that accomplishes movement. 1. Display the image using the code that creates the image. 2. Change the color of the pen to the same color as the background color that you are drawing on. 3. Redraw the image in the background color. The object will have seemed to disappear. 4. Delay the computer. 5. Change the pen back to the original color. 6. Redraw the image using new points for positions. Every time you move the object, you need to match its color to the background. color to erase it, and then redraw it in a new position. Delaying the computer. Nowadays, most computers' microprocessors are so fast that the computer will be able to execute your program very quickly. In the case of moving an image, the computer will execute your instructions perhaps too quickly, to the point that a viewer will not recognize what you are trying to do. Before you are able to give the appearance of movement, you will need to control the speed of that movement. What we want to do is delay the computer or slow it down. One of the easiest ways to do this is give it an empty for loop to execute. This is the name I give to a for loop that spins but does nothing. Think of the analogy of lifting the back bicycle wheel and then turning the pedal. You see the wheel spin, but the bike can't go anywhere because the wheel is not on the ground. So you write the code for the for loop, but the loop itself is empty. That is, the body of the loop has no programming statements. The compiler then spends time setting the initial variable, checking the Boolean condition using that variable, and then increasing the value of the variable. It repeatedly does these 3 steps, but because there is nothing to do inside the loop itself, the user does not see anything happen on the screen. The computer is, in effect, spinning its wheels and being kept busy. After delaying the computer, we can allow the computer to do the next thing. Examples. Let's look at the syntax of an empty for loop. We will set the conditional variable to 1 in each example, but we will change the upper limit used in each Boolean condition. The higher the upper limit, the more times the loop spins. For int x is equal to 1, x is less than 1000, x is equal to x plus 1. For int x is equal to 1, x is less than 1000, x is less than 10,000, x is equal to x plus 1. In the first example, the loop spins 1,000 times. That's a lot. However, in the second example, the loop spins 100,000 times. Must have misspoke there. That's really a lot. Notice in each example that a semicolon follows immediately after the statement to show that the loop ends right away. This design shows that the loop is not controlling any other statement. It has no statements called the body of the loop to spin. The best way to see the results of using an empty for loop is to run your program without this loop. If what you see appears to be happening too fast, then maybe you will need to slow down the program. This loop can be helpful for you. When you become a more experienced programmer, you can also write code to access the clock function, which will return the time elapsed in number of ticks from the beginning of the processing in the program. Accessing this time will allow you to more accurately occupy the processor. There is a constant called CLK-TICS, CLK-TICS, which tells you how many ticks occur per second. On many computers, this number will be 1000. If you take the number of ticks per second and multiply the number of seconds you wish to delay the processor, you will get a new number that can be used with the elapsed processor clock time of the CPU. Look at this example. Clock T first time equals clock. The present elapsed ticks of the processor double M equals 3 times CLK-TICS. The number of ticks needed to equal 3 seconds, while clock minus first time is less than M. The empty loop, which will execute until the present number of ticks exceeds the number needed for 3 seconds. Using functions to draw. Most applications of a programming language will provide some graphics capabilities in the form of a toolbox or a library of functions. You need to access that library and look at those functions. The frustrating thing, however, is finding out what functions have been provided for you. The frustrating thing, however, is finding out what functions have been provided for you for your use. Depending on what version of what language you purchase, your graphics functions will be specific to that version and the hardware on which you run your programs. You need to look at the functions themselves and examine their headings, just like we did with move-to and line-to. Once you understand what parameters, the variable types each function needs, and what each function does, then you can make decisions about how you wish to draw some object. In this section, we will examine some generic functions that are simulated in languages that provide graphics capabilities. You might be able to use these exact same functions or something like them. Pen size takes the height and width of the pen. Full color allows you to set the color of the foreground. Set rect sets the coordinates of each of the corners of a rectangle, but does not draw it. Frame rect draws the outline of the rectangle. Paint rect paints the rectangle with the full color you choose. Frame oval outlines the circle. Paint oval fills the circle with a color. First, I'll need to explain how each of these functions work. Then you can use them to make whatever drawings you wish. A rectangle has four sides. It is a special type of variable whose syntax I will explain in chapter 11 when you learn about a struct I won't forget. Each side of the rectangle has a name that represents either a row or a column. See figure 9.7. Figure 9.7. Each side has been named and drawn as either a row or a column. where top and bottom are rows and left and right are columns. Both the top and bottom of the rectangle are rows, which you need to estimate depending on the size of the screen on which you are drawing. Both the left and right sides of the rectangle are columns that you position. There are two things to consider when you construct a rectangle: its position relative to the screen and its dimensions, width and height. If a screen is 400 rows by 600 columns, then you might want to position a rectangle in the middle of the screen. You would start to think about being at row 200 and column 300. If you want the rectangle to be 50 units wide and 100 units long, then you need to consider the following positions. The right side of the rectangle should be at column 350. If you want the rectangle to be 100 units long, then you should set the bottom of the rectangle to be 100 units below row 200 at row 300. The difference between the two sides, left and right, of the rectangle is 50 units, 350 minus 300. The difference between the other two sides, top and bottom, is 100 units, 300 minus 200. Every time you construct a rectangle, you need to consider where you will position it and then how to adjust the sides of the rectangle so that they have the appropriate dimensions you want. Once you decide which rows and columns you will use for your rectangle's sides, then you set their values by calling the setRect function. You need to follow the heading given in setRect, which might look like this: void setRect rect times r int top left bottom right. Notice that the parameters of the function are all integers except for the first parameter, which is a rect. But what is a rect? It is a special variable called a pointer variable, which we will examine later in chapter 17. For now, just think of it as a rectangle and follow the syntax used in the example. We want to make a call to setRect, but we don't have any names for the rectangle yet. So let's call it by this name, house, and we will declare it in the following manner. Rect times house, use the multiplication sign in between the rect and its name. Next, we make the call by using the integers that comprise the sides of the rectangle. Top equals 200, bottom equals 300, left is equal to 300, right is equal to 350. Our call would be this: setRect, house, top, bottom, left, right. Notice that in the call, there are no types mentioned, i.e. int or rect. Star. Only the names of the variables are used. After calling this function, the rectangle is ready to be drawn, since all its coordinates have been set. Now to draw it, we need to call another function, frameRect. FrameRect has only one parameter, the rect itself, r. Let's look at its heading. Void frameRect rect times r. Now we will call frameRect in the main program using our rectangle called house. Notice that since the function is a function that does not return anything, note the word void, the call looks like this. Frame rect, house. The next thing you should do is fill in the house with some color so that it is not just an outline of a house. We will call the function paintRect next. Here is its heading and the call we should use with it. Notice the differences in syntax between the heading and the call. In the tables that follow, each part of the function heading is separated so you can understand the syntax better. First, the return type of the function is listed, followed by the function name, and then what parameters it requires. Recall from Chapter 8 that all functions must indicate what they return as a value. If they don't return a value, the word void is listed. All functions have names so that they can be called, and usually they require some variable to work on. This variable is called a parameter. Void paintRect, rect times r, function heading. Return type void, function name paintRect, parameter type rect multiplication sign, parentheses begin here, parameter name r, and end here. Next, the function call is listed in a table so that you can see the syntax is almost the same as the heading. Because the return type was void, as listed previously, the call is made with the function name only and the parameter it requires, which we saw was a rect type variable. paintRect house, function call. Return type none, expected. Function name paintRect, actual parameter house. Caution. Calls always differ from headings because the type of variable is not mentioned in the call, only the name of the variable. The compiler will know what type is being sent in because it has already translated the heading. Now let's take care of some of the smaller details that we need to consider. Following is a list of typical colors from which you can choose. We will pick a color with which we will draw the house. Let's pick black. Cyan, magenta, green, red, yellow, blue, black, white. Let's look back at the heading that set the color for the drawing. It was called forecolor. It sets the color in the foreground, the area where we are drawing everything. For the second time, you will see an unfamiliar type. After the rect multiplication sign type we saw in set rect, we are now seeing the color type. Think of the color type as a built-in type that is independent of the language. It really was defined for the sake of the computer's hardware. Since we need to pay attention to syntax, let's follow the syntax given in forecolor's heading so that we can make an appropriate call. Here again, we list the elements in a table so that you can better understand the different parts of the function heading. Void, full color, color C, function heading. Return type, function name, parameter type, parameter name. Turn type, void, function name, color, full color, parameter type, color, parentheses begin here, parameter name, C, and end here. Full color, black, function call. Return type, none, expected. Function name, full color, actual parameter, black. One last detail is to set the size of the pen with which we are drawing. The pen tip size is measured in height and width. Let's set the width of the pen tip to be 4 units wide by 6 units long. Look at the following table to see different elements of the function here heading. Void, pen size, int height, int width, function heading. Return type, void, function name, pen size. Parameter type to int, parentheses begin here, parameter name, height, width, and end here. Pen size 4, 6, function call. Return type, none, expected. Function name, pen size. Actual parameter, 4, 6. Notice that in the call to pen size, I did not use any variables, only the direct values 4 and 6. We can do this when we are using value parameters. Recall that the function just needs the values of the variables, not the variable holder, not the variable holders themselves. Now we will put together all the separate parts into one program fragment in the main functions. Rect times house, int top, bottom, left, right, top equals 200, bottom equals 300, left equals 300, right is equal to 350, pen size 4, 6, full color black, set rect, house, top, bottom, left, right, frame rect, house, paint rect, house. That should draw a house that looks like figure 9.8. Figure 9.8. A black rectangle is shown representing a house. So in your algorithm for drawing any object, you need to set the color of the objects being drawn. You will probably have to change the color each time you draw something new. Drawing the sun by using the oval commands. Next, if we wish to draw the sun in the sky, for example, we need to call a function that allows us to draw a circle. Circles are drawn through oval functions, which are functions that can draw any oval of any size specified. The size of the oval is determined from a circumscribed rectangle, that is, a rectangle drawn around the oval. First, the rectangle's size is set according to the previous sides mentioned: top, bottom, left, and right. Then the largest possible oval, one that touches all sides, is drawn to fit inside of the rectangle. See figure 9.9. Figure 9.9. Two rectangles are shown empty and then with the largest oval that fits inside each. In the second example, the oval is a circle in a sense the rectangle is... In the second example, the oval is a circle since the rectangle in which it is drawn is a square. Here are the headings of a couple of oval functions. By using the setRect function that you saw previously, you can set the coordinates for the sides of the frame of the rectangle, and then call on the oval commands to actually draw the oval. Here are the headings of the oval functions: void frame oval, rect times r; void paint oval, rect times r. Before calling setRect, we will see the coordinates of the rectangle in which we will draw the oval representing the sun. We will position it above the house and to the left of it by using the values that follow. Rect times sun, int top, bottom, left, right. Top is equal to 75, bottom is equal to 100, left is equal to 200, right is equal to 225. We will change the fore color to yellow so that it looks appropriate. For color, yellow. Set rect, sun, top, bottom, left, right. Frame oval, sun. Paint oval, sun. Examining the rectangle's width, you can see that it is 25 units wide, 175, and the length is also 25 units long, 225 to 200. This demonstrates that the rectangle is really a square, 25 units by 25 units. So the oval drawn inside that square will be a circle. Just from these two examples, you can see that it is a lot of work to call on these functions to draw objects. You also need to work within the parameters specified by the function. Imagine that drawing a circle involves designing a rectangle that is really a square, so that an oval drawn inside it appears to be a circle. That is complicated. The good part about these functions is that they are good practice for working within a function's parameters. Summary. First, we began by defining graphics as programming the computer to draw shapes. We introduced a type called vector graphics, where lines are drawn with direction in mind. A line is always drawn from an initial position to a new position where it ends, and for this reason is an example of the vector directed graphics. Most graphics will be drawn by calling functions that do the work for you. The only thing to be careful about is what type of parameters each function needs to operate properly. Functions will vary from language to language and will also be dependent on the operating system used. The first two functions we examined were line_to and move_to, used to draw lines from your present position to a new position and for moving to a new position. There are certain tricks that allow the programmer to make a drawing disappear. The first point is to draw the shape and then redraw it in the background color. That has the effect of erasing it. Then move the shape by drawing it in a new position. Every time you want to move, you have to draw it in the background color so that it can disappear. If any of these tricks are executed too quickly by the computer, there is an additional tactic to be if any of these tricks are executed too quickly by the computer, there is an additional tactic to be employed: delaying the computer. This is done by inserting an empty for loop to make the computer spin its wheels. There are many graphics functions that allow the programmer to draw different shapes on the screen. By calling these functions properly, the programmer only has to decide where a particular shape should be drawn. The screen is divided into rows and columns. Depending on the number of rows and columns visible on your screen, you will position shapes accordingly. Rectangles are used in many of these functions and consist of a top and a bottom, both of which are rows, and a left and a right, both of which are columns. Functions like setRect, frameRect, and paintRect will see the size of the rectangle, then draw its outline and fill it in with the foreground color. The oval function frameOval and paintOval, oval functions rather, frameOval and paintOval, are extensions of these rectangle functions that allow the largest possible oval to be drawn within a rectangle whose position is set by the programmer.